Now we continue proving the result that I stated in the beginning of the last installment of the lecture, and that is that if f and g are integrable on AB, then f plus g is integral on AB, and the integral of f plus g is equal to integral of f plus integral of g. Let's see. Okay, so that is going to be part 2. So we suppose that f and g are integrable on AB. Then, by the first criterion of integrability, we know that given an epsilon greater than 0, there exists a partition PF such that U of F PF minus L of F PF, in this case I would want this to be less than epsilon over 2, and there exists another partition of AB let's call it PG, such that U of G PG minus L of G PG, that this is less than epsilon over 2, right? I'm just writing the first criterion of integrability for both functions f and g. Okay, so then it is easy to see that P equal to PF union, PG, that this is a partition of AB, which defines both PF and PG, right? This is a partition which is finer than both PF and PG. And then by the theorem that we proved a couple of lectures ago, what happens to an upper Darboux sum if I define an interval? Upper Darboux sum or overestimation goes down, lower Darboux sum or underestimation goes up. So then the difference of the upper and lower Darboux sums should decrease. Right, because U decreased, L increased, so the difference should go down. So therefore, what we're getting, because P is a refinement of PF, then U of FP minus L of Fp, this should be less or equal than U of FPF minus L of FPF, which we know already is less than epsilon over 2. Right, and likewise, u of g, p, minus L of gp, this is less or equal than u of g pg minus L of gpg, again, due to this theorem about refinement. And that is also less than epsilon over 2. Okay, so with this in mind, now let's work with the partition P. And what I would like to do is I would like to compare the following. So next, we want to estimate for the partition P that we found, we want to estimate u of f plus g, of the sum of two functions over the partition P, minus Lord-Darboux sum of f plus g over the partition P. If we can show that this is less than epsilon, then we're done, because then f plus g satisfies the first criterion of integrability. Okay, so we're going to notice the following two facts. Let's say I take M, capital M, of f plus g over some interval ti minus 1 to ti. Well, what is that? That is a supremum when t is between ti minus 1 and ti of f plus f of t plus g of t. Again, at some point in the past, we demonstrated that if you take a supremum of a sum of two functions, then the supremum of a sum must be less or equal than sum of the suprema of the functions, which is sort of easy to comprehend, right? So obviously, f plus g, I'm not going to write this down as a proof again, you should be able to try it yourself, but the hint is that if I take supremum of f of t, it's a number which is larger than any f of t on the interval from ti minus 1 to ti. I take a supremum of g of t, that certainly is the largest possible choice of g on that interval. So then f plus g automatically should have a value which is lower than the largest value of f plus the largest value of g. So this should be less or equal than supremum t between ti minus 1 ti of f of t plus the supremum t between ti minus 1 and ti of g of t. And what are those? What notation have we used? Have we been using actually for the supremum of the function on the interval from ti minus 1 to ti? The first supremum then is capital M of f ti minus 1 ti. And for g, again, it's a capital M, but now of g ti minus 1 ti. Okay, so if that is the case, if capital M splits like this, then what is going to happen to capital U of f plus g of the partition P, that is a sum I from 1 to n, capital M of f plus g ti minus 1 ti times ti minus 1. And then capital M is less or equal than the sum of m's for individual two functions, for f and g. So from this, I can immediately see that this is less or equal than sum from 1 to n m of f ti minus 1 to ti times ti minus ti minus 1 plus the same thing for g. So g here. And now if I inspect this expression, then I can see, of course, that the first sum is exactly u of fp, and the second sum is u of gp. All right? And in a similar fashion, we can establish a similar inequality for L, and that inequality will say that L of f plus g comma p, what do we expect? With suprema, u of f plus u of g is bigger than u of f plus g, then with infima we would expect that L of f plus g is greater or equal than L of fp plus L of gp. Okay? Fine. So then, what was I trying to estimate? I was trying to estimate u of f plus g p minus L of f plus g p. So now what do I know? I know that this is going to be less or equal than u of f plus g comma p. This is less or equal than u of fp plus u of gp. At the same time, L is going to decrease, right? So L of f plus g is greater or equal than L of f plus L of g. But if I multiply both sides of this by minus 1, then the sign of inequality will change. So minus L of f plus gp is going to be less or equal than minus L of fp minus L of gp. So I can put minus L of fp minus L of gp on the right hand side here. All right. And so then I can recombine terms. This is equal to u of fp minus L of fp plus u of gp minus L of gp. And if you remember by my regional assumptions, I chose p in such a way that this difference is less than epsilon over 2, and this difference is less than epsilon over 2. So this is less than epsilon over 2 plus epsilon over 2, which is epsilon. And so then the conclusion is that f plus g is integrable on AB by the first criterion of integrability. Okay, so we showed the half of this, we proved the half of this statement. We also have a second half, that the integral of f plus g is equal to the integral of f to the integral of g. So next we need to show that integral from a to b of f plus g is actually equal to the integral from a to b of f plus the integral from a to b of g. And we're going to do it in the following way. So I'm going to produce the following chain of inequalities, and I'm going to use take advantage of the same partition P that we used in the previous statement. So here is how I'm going to proceed. Well, so I take integral from a to b of f plus g. Now, what is that? I know that f plus g is integrable, so this should be equal to u of f plus g, right? It's equal to actually both u of f plus g and L of f plus g. Now, who is u of f plus g? That is upper Darboux integral, which is equal to the infimum of upper Darboux sums. So for my upper Darboux sum of the partition P, that object must be greater or equal than u of f plus g, right? So this is less or equal than u of f plus g, p, right? Because, again, upper Darboux integral is an infimum of u of f plus g. And what do I know about u of f plus g p from my previous statement is that u of f plus gp minus L of plus gp, that this is less than epsilon, right? So if I solve this for u of f plus gp, I get u of f plus gp is less than L of f plus gp plus epsilon. Let's see, actually, yes. Let me see, what am I going to try to say here? Okay, so that's fine. So, actually, before doing this, let me do something else. What I know about u of f plus gp, one thing that I know about it, is that it is less than a sum of u of fp and u of gp. So let's use that first. So this is less or equal than u of fp plus u of gp. And now I'm going to use what we know about u of fp versus L of fp. So it would be a similar expression to this one, right? We had let me go back to it again. So u of fp minus L of fp is less than epsilon over 2. So if I add L of fp to both sides, u of fp is less than L of fp plus epsilon over 2. So this is less than L of fp plus epsilon over 2. And likewise for u of gp minus L of gp is less than epsilon over 2. So u of gp is less than L of gp plus epsilon over 2. Okay? All right, so then I will remember that a lower Darboux sum is related to lower Darboux integral in what way? Lower Darboux integral is a supremum over lower Darboux sums. So if it is supreme over all possible lower Darboux sums, that means that this should be less or equal than L of f, right? L of fp is less or equal than L of f. L of gp is less or equal than L of g. And of course, epsilon over 2 plus epsilon over 2 gives me plus epsilon. And then the final step here, what is L of f? Because f is an integrable function, L of f is an integral from a to b of f. Likewise, L of g is an integral from a to b of g. And then we have this plus extra epsilon that is hanging around. Okay, so we get this. So this is not exactly what I intend to show, right? Because what we got is that integral from a to b of f plus g is less than the sum of the integrals plus epsilon. Now, remember that we said before, an epsilon here is just some random epsilon that I picked in the beginning. So that means that if I let epsilon go to 0, then this allows me to conclude that integral from a to b of f plus g, that is going to be less or equal than integral from a to b of f plus integral from a to b of g, right? Just by sending epsilon to 0. Okay, so it's just a half of what I wanted to show, because I want to show that both sides of this last inequality are exactly the same. So to make them the same, I have to prove the opposite inequality, that the integral of f plus g is greater or equal than the sum of two integrals. And I can try actually exactly the same approach as I did above. For some reason, when I made the first step in this calculation, I said that integral of f plus g is equal to u of f plus g. But of course, for an integrable function, u of f plus g and L of f plus g are the same. So I'm going to start with saying that u of f, that the integral is equal to L of f plus g. Okay, L of f plus g is related to, so lower Darboux integral is related to lower Darboux sums. In what way? Lower Darboux integral is a supremo of lower Darboux sums. So that means that this should be greater or equal than L of f plus g. And I go back to my partition P, so it's a lower Darboux sum for the partition P, right? That gave me epsilon at the end of the day. All right, so what about that? We figured out before that L of f plus g p must be greater or equal than L of fp plus L of gp. Okay, so I'll use that here. This is greater or equal than L of fp plus L of gp. And then again, if I look at this statement up here, what does this tell me? It tells me that u minus L is less than epsilon over 2, right, for f. Well, if I then move L to the right side of the inequality, and I move epsilon over 2 to the left side, what I get is that L is greater than u of fp minus epsilon over 2. So the sum down here is greater than u of fp minus epsilon over 2. And for LGP, exactly the same inequality held. So L of GP should be greater than U of GP, again, minus epsilon over 2. Okay, fine. So now, how is U of FP related to U of F? Upper Darboux sum, how is it related to upper Darboux integral? Upper Darboux sum is larger because upper Darboux integral is infimum of upper Darboux sums. So then this must be greater or equal than U of F, right? U of Fp is greater than U of F. U of Gp is greater than U of G. And then we have 2 epsilon over 2 that we're subtracting, so minus epsilon. And then the last inequality, what is this thing here? This is f is an integrable function, so U of f is the same thing as the integral from a to b of f. U of g is the same thing as an integral from a to b of g, and then epsilon still is sitting here. And just like I did this before, epsilon in this computation is a randomly chosen number in the beginning. So I can send this number to 0, and that will give me that the integral from a to b of f plus g must be greater or equal to the integral from a to b of f plus the integral from a to b of g. And that's exactly what I needed, right? Because now this is the same inequality in both cases, except that sign of the inequality is different. And so that means that from here and from here, we get that the integral from a to b of f plus g must be the same as the integral from a to b of f plus the integral from a to b of g. And the statement is proved. Okay, so we move on now to the next property. And the next property is going to be, let me see how I labeled this one. Okay, so this would be property 4. It is going to be the following. If f and g are integrable on AB, and f of x is greater or equal than g of x for all x in AB, then the comparison result holds. Integral from a to b of f is less or equal than the integral from a to b of g. So let's prove this. And the trick here is to look at the function g minus f. So let's define h to be g minus f. Now, in a previous couple of items, we proved that if I multiply a function by minus 1, that function is going to integrable a function by minus 1. That function is still integrable. And if I add two functions that are integrable, I get a function that is integrable. So f is integral on AB, therefore minus f is integrable on AB, therefore g plus minus f is integrable on AB, but g plus minus f is g minus f. So by 3, h is integrable on AB, and even more, integral of h is equal to the integral from a to b of g minus integral from a to b of f, right? Okay, so further, if I look at the values of h between when x is between a and b, h of x is equal to g of x minus f of x. And because we assume that f of x is always less or equal than g of x, then h of x is always greater or equal than 0 for all x between a and b. Okay, so h is an integrable function. It is greater or equal than 0. So what can I conclude from that? I can conclude the following. I can conclude that if I'm computing, so for any partition P, if I compute L of Fp, again, L of Fp is equal to sum I from 1 to n, little m, ft I minus 1 ti times ti minus ti minus 1. Well, if this is not f but h, sorry. So what I know about h is always non-negative, right? Which means that m, the infimum of the function that is always non-negative, must also be non-negative, right? Because ti is greater or equal than ti minus 1. Of course, this is also a non-negative number. In fact, it's strictly positive. And so then the sum must be greater or equal than 0. And this is true for any partition P. And so then, if I compute L of h, which is a supremum over all p's of L of hp, if all L of hp's are greater or equal than 0, then supremum of the numbers that are greater or equal than 0 is a number that is still greater or equal than 0. But then, because we proved that h is integrable on AB, we already showed that, it follows that the integral from a to b of h, which is equal to L of h, that this integral is greater or equal than 0. Okay? Well, but then we established already this relationship between the integrals of h, g, and f. So therefore, the integral from a to b of f minus integral from a to b of g, I'm just writing this expression backwards, which is equal to the integral from a to b of h. This is greater or equal than 0. And so because of that, integral from a to b of f is greater or equal I, is less or equal, let's see, what am I doing here? What am I doing here? I wrote them backwards, sorry. Integral of g minus integral of f. So integral of g must be greater or equal than the integral from a to b of f, and that's what we wanted to show. Okay, so then from this I would be able to establish more properties. Property number 5. Let's suppose that f of x is greater or equal than 0 on AB, and the integral from a to b of f is equal to 0. Now, if I'm writing that the integral from a to b of f is equal to 0, that means automatically that I assume that the function f is integrable. So then you have a trivial looking statement. Then it follows that actually there is one more thing that I want to assume. Let me just move this. I'm also going to assume that f is continuous on AB. So we have these 3 statements. Then from here, we should be able to show that f is identically equal to 0 on AB. Right? F of x is equal to 0 for all x on AB. That's just a different way of writing this down. Now let's prove this. Well, so let's try to use a contradiction here. Suppose that f of x 0 is not equal 0 for some x0 between a and b, right? Now, because the function is continuous, there exists, let's say, a delta greater than 0, such that if x minus x0 is less than delta, then f of x minus f of x0 is less, and as my epsilon, I'm going to choose f of x0 over 2. Right? Okay, but writing this, if I remove absolute value sign, so this is equivalent. To the following: if x minus x0 is less than delta. In fact, let me write this in a slightly different way. I'm going to remove the absolute value sign. If x minus x0 is less than delta greater than minus delta, we have that, and I'm going to remove the absolute value sign here as well. So minus f of x0 over 2 is less than f of x minus f of x 0 less than f of x0 over 2. So this, again, implies the following thing now. And I'm just rewriting. If I add x0 to all three sides out here, I'm going to get if x0 minus delta is less than x less than x0 plus delta, we have, and in this case I'm going to add f of x0 to all three sides. And if I add f of x0, I'm going to get f of x0 over 2 less than f of x. And in fact, I'm going to ignore the upper side of the inequality. So that's the only thing that I really need here. So if x belongs to an interval around, let me see if I can manage this box. Okay. If x is between the x0 minus delta and x0 plus delta, we're guaranteed that f of x is greater than f of x0 over 2. Well, but then if I look at the function, so let's define the function. So if we set g of x to be the following, it's 0 if x does not belong to the interval from x0 minus delta to x0 plus delta. So if you're not in this interval, the value of the function g is going to be 0, and if you are in this interval, then the value of the function is going to be f of x0 over 2 if x is between x0 minus delta and x0 plus delta. So what can we say about the function g of x? Well, when g of x is equal to 0, f of x, we assumed is greater or equal than 0. So f of x is greater or equal than g of x on this interval. And when x is between x0 minus delta and x0 plus delta, then we know that f of x is bigger than f of x0 over 2. So in that interval, f of x is also greater than g of x. So then f of x is greater or equal than g of x on the entire interval AB. And f is an integrable function. And it's easy to show that g is also an integrable function. I'm not going to do it, but it's easy to see that it is going to be integrable. And from that, in the previous statement, so that would be the statement number 4, we conclude that the integral from a to b of f is greater or equal than the integral from a to b of g. But the integral from a to b of g, this is something that I would like you to verify. Actually, that integral, right, is an integral of a function which is not 0 only between x0 minus delta and x0 plus delta, right? So only the values there are going to contribute x0 minus delta, x0 plus delta. And there, the function is equal to f of x0 over 2, which is a constant, which is going to give you f of x0 over 2 times the length of the interval from x0 minus delta to x0 plus delta, and then of course the length of that interval is going to be 2 delta. So we have 2 delta times f of x0 over 2, delta times f of x0. And both delta and f of x0 are positive numbers. And so therefore, this quantity is going to be strictly greater than 0. Right? Delta of x0 is bigger than 0 because delta automatically is a number greater than 0. And f of x0 we assumed is not 0, it's positive. So this is greater than 0. And this is a contradiction because